Hi dear students, today we are going to discuss one of the very important concepts of electrochemistry, that is Nernst equation. Nernst equation. First, before going to discuss about Nernst equation, let's discuss one small concept that we have already discussed. Suppose if you take a vessel in which some salt solution is filled, say for example a vessel is filled with zinc sulfate solution. Zinc sulfate solution consists of a huge number of zinc ions as well as sulfate ions in their aqueous form. Right. If we keep a zinc metal rod into the zinc sulfate solution, zinc metal rod consists of a huge number of zinc atoms. Here we know that zinc atoms have their own potential and zinc ions inside the solution have their own potential. When both are in contact with each other, there exists some potential difference. That potential difference is called electrode potential. This all we have discussed in previous lecture. Now, here practically it was observed that when the concentration of this electrolytic solution changes, so for example, if this concentration is 0.5 m ZnSO4 solution, then electrode potential of zinc is different. When we take some other concentration like 1 m ZnSO4 solution, then the concentration of then the electrode potential of zinc metal rod will be different. That means the electrode potential of a particular electrode depends on molar concentration of the electrolytic solution. This was the observation made by Nernst. So based on this observation, Nernst has derived an equation called Nernst equation. To understand Nernst equation, first let us take a reduction reaction. So for example, M is a metal, its valency is N. It gains n number of electrons to become neutral, solid. This is aqueous metal ions, valency is plus n. This is generalized form, you no need to worry about this. To understand better, so let us take our previous examples. From our previous examples, Cu plus 2, copper metal ion, valency is 2, it gains 2 electrons from cathode. Then it becomes a neutral copper metal atom, right? It's very similar to this. This is a generalized form. Here n is an integer. It may be 1, 2, 3, 4 based on the valency of the metal, right? Now let us apply Nernst equation to this generalized form. So according to Nernst, reduction potential of an electrode at a given temperature is equal to standard reduction potential minus RT by NF ln molar concentration of metal by molar concentration of metal ions in their aqueous form. This was a relation given by Nernst. Here let us see once again what is this. This is electrode potential of the electrode at a given temperature. Here E naught m plus bar m, this is nothing but standard electrode potential of the metal. At a given temperature T. Here E naught is the standard electrode potential. The standard electrode potential is a known value. The standard electrode potentials can be calculated by using reference electrode like hydrogen electrode, standard hydrogen electrode that we have discussed in previous lecture. Right. Next here R is a gas constant. Its value is 8.314 joules per mole per Kelvin, and T is absolute temperature. T is absolute temperature. N is number of electrons transferred. Number of electrons transferred. Just to understand this, see this example. Here how many electrons getting transferred? 2 electrons. Thus for this type of reactions, here N value becomes 2. And finally F is Faraday. F is Faraday. Its value is approximately 96,500 coulombs per mole. Right? Here molar concentration of metal is given in the equation. Here molar concentration of metal is given. Actually molar concentrations of solids is taken as unity, that is 1. Molar concentration of solid is always equal to 1. So here this is a metallic form or solid form, so its molar concentration becomes 1. Then the above Nernst equation is modified as reduction potential of a given electrode is equal to standard reduction potential minus RT by NF ln 1 by molar concentration of the metal ions in aqueous form. Here ln means natural logarithm. Ln is natural logarithm. Natural logarithm can be converted to logarithm to the base 10 by multiplying with 2.303. Ln is equal to 2.303 log to the base 10. So here if you take the temperature, that is room temperature 298 Kelvin temperature, R value is 8.314 joules per mole per Kelvin, and so we get reduction potential of an electrode is equal to standard reduction potential minus 8.314 into temperature we have taken as 298 Kelvin, that is room temperature, by N into 96,500, that is 1 Faraday, ln 1 by molar concentration of the M plus ions. Right. Now here this logarithm is natural logarithm. Just I told you natural logarithm can be converted into logarithm to the base 10 by multiplying with 2.303. So that can be written as E naught M plus N by M minus 2.303 into 8.314 into 298 by N into 96,500 log 1 by M plus N concentration. So what are the changes? Here instead of ln I have written 2.303 into log. So here you can find some values: 2.303, 8.314, 298, 96,500 in the denominator. On simplifying all these values, finally we get standard reduction potential minus 0.059 by N log 1 by M plus N concentration. So what is this 0.059? This 0.059 is nothing but it's the value of modified value of 2.303 into 8.314 into 298 by 96,500. If we simplify this, finally we get approximately 0.059. Right, this is the final modified form of Nernst equation. That means here from this form what you can understand, electrode potential of a given electrode electrode potential of a given electrode is equal to standard electrode potential or standard reduction potential minus 0.059 by n log 1 by m plus n concentration. This is a generalized modified Nernst equation. Now let us take a galvanic cell as an example. What are the reactions taking place in galvanic cell? Okay, there are two reactions taking place, that is Zn gives Zn plus 2 electrons, and a Cu plus 2 electrons gives Cu. These reactions we have already discussed in the previous lecture. So these are the reactions. Now let us apply Nernst equations to these two reactions individually. The first one, E Zn plus 2 bar Zn. So instead of M, I am writing Zn metal, zinc metal, and standard reduction potential of zinc minus 0.059 by 2. Why I am using 2 here? So here in the given formula, N is there. N. What is N? N is number of electrons transferred. How many electrons get transferred here? During this oxidation process of zinc, 2 electrons. So I have written 2 log 1 by Zn plus 2 concentration, molar concentration of Zn plus 2 ions. Okay, let it be equation number 2. Now similarly, electrode potential of copper, reduction potential of copper or electrode potential of copper is equal to standard electrode potential of copper minus 0.059 by 2. Here also I am writing 2 because here also number of electrons transferred is 2 into log 1 by Cu plus 2 concentration, molar concentration of Cu plus 2 ions. Let it be equation number 3. Now here equation 2 and 3 are the reduction potentials of zinc and copper respectively. Now from these two values we can able to determine total cell potential. Total cell potential we already discussed in a galvanic cell. We use a zinc rod and a copper rod, both are connected with external wire. Here there is a salt bridge. This is ZnSO4 solution, and this one is copper sulfate solution, CuSO4 solution. This is a half cell, this one is another half cell. This half cell potential we have determined now. This is the half cell potential, that is E Zn plus 2 bar Zn. ECU plus 2 bar Cu is the remaining half cell reaction. That means this is cathodic reduction potential and this one is anodic reduction potential. If we know cathodic reduction potential and anodic reduction potential, from that we can able to determine the total cell potential. For that we have a formula, that is total cell potential E cell is equal to electrode potential of cathode minus electrode potential of anode. So what is cathode and anode in a galvanic cell? In a galvanic cell, the right side part is cathode, that is copper in copper sulfate solution acts as cathodic compartment, and remaining zinc in zinc sulfate solution acts as anodic compartment. So here on substituting equations 2 and 3 in this formula, then we get electrode potential of the cell is equal to, first electrode potential of cathode. Cathode is copper, so E naught Cu plus 2 bar Cu minus 0.059 by 2 log 1 by Cu plus 2 concentration minus E anode, that is anode is zinc in zinc sulfate solution, that is minus standard electrode potential of zinc minus 0.059 by 2 log 1 by Zn plus 2 concentration. Okay, here the standard electrode potentials can be taken as common. Then standard electrode potential of copper minus standard electrode potential of zinc. Okay, this is taken as common. Here minus 0.59 by 2 minus 0.059 by 2 minus 0.059 by 2 is there, so it also can be taken as common, minus 0.059 by 2. If we take this as common, then the remaining part is here log 1 by Cu plus 2 concentration minus log 1 by Zn plus 2 concentration is left. Here it can be seen like log A minus log B. Log A minus log B can be written as log A by B. Okay, I'll see that later. Now here you see standard electrode potential of copper minus standard electrode potential of zinc can be written as standard electrode potential of the cell. Why? Here what is the electrode potential of cell? Electrode potential of cell is equal to cathode potential minus anodic potential. Here also this is just like standard cathodic potential minus standard anodic potential means standard cell potential. Standard cell potential minus 0.059 by 2. So this is in the form of log A minus log B, no? On modifying this, see this is here what is A? 1 by Cu plus 2 concentration, no? 1 by Cu plus 2 concentration by 1 by Zn plus 2 concentration. So this is in the form of A by B by C by D. So this can be written as 1 by Cu plus 2 concentration into this 1 by Zn plus 2 concentration can be written as Zn plus 2 concentration by 1. So this part becomes Zn plus 2 concentration by Cu plus 2 concentration. So log Zn plus 2 concentration, molar concentration of Zn plus 2 by molar concentration of Cu plus 2. So this is, see here, E cell is equal to E naught cell minus 0.059 by 2. This is the modified form of Nernst equation for the galvanic cell. This is for complete cell reaction. This is for complete cell electrode potential. Electrode potential of the cell is equal to standard electrode potential of the cell minus 0.059 by 2 log Zn plus 2 concentration by Cu plus 2 concentration. Log molar concentration of anodic solution by molar concentration of cathodic solution. This equation is very important, and it is very much helpful for most of the numericals asking based on Nernst equation. So derivation part is very important. Now let us discuss equilibrium constant from Nernst equation. Equilibrium constant from Nernst equation. Now let us discuss equilibrium constant from Nernst equation. So before going to that, let's have a small introduction. So if you take a galvanic cell, in one cell will take ZnSO4 solution, and in another cell will take copper sulfate solution. Zinc rod, copper rod, both are connected through external wire, and there is a salt bridge. So it was observed that in the beginning of the process, the concentration of Zn plus 2 ions gradually increases, concentration of Cu plus 2 ions gradually decreases. This is because the zinc metal get dissolved and releases Zn plus 2 ions into the solution, whereas in case of cathodic compartment, Cu plus 2 ions of the solution get deposited on the surface of cathode, so that the Zn plus 2 ions, concentration of Zn plus 2 ions gradually increases, concentration of Cu plus 2 ions gradually decreases. But at a certain point of time, both the molar concentrations becomes equal, that is molar concentration of Zn plus 2 becomes equal to molar concentration of Cu plus 2. That situation is called equilibrium. When both the molar concentrations becomes equal, then in that situation the potential of the cell becomes 0. The total potential of the cell becomes 0. That means E cell is equal to 0. Cell potential becomes 0. That means at equilibrium condition, the cell potential becomes 0 because there is no movement of electrons through the external circuit. Right. If we apply that condition, this equation, let it be equation number 4. This equation number 4 is modified as, here what happens? Electrode potential at equilibrium, okay, I am writing here, at equilibrium, cell potential E cell becomes equal to 0. Then equation number 4, equation 4 is modified as 0 is equal to standard electrode potential of the cell minus 0.059 by 2 log Zn plus 2 concentration by Cu plus 2 concentration. So here 0 is equal to this one. So if we send this part, that is minus negative part, to the left hand side, then it becomes standard electrode potential of the cell is equal to 0.059 by 2 log Zn plus 2 concentration by Cu plus 2 concentration. So this is the modified form. Here Zn plus 2 concentration by Cu plus 2 concentration means molar concentration of anodic solution by molar concentration of cathodic solution. This gives a constant called equilibrium constant. So this can further modified as E naught cell is equal to 0.059 by 2 log Kc. Here Kc is equilibrium constant, that is equal to molar concentration of Zn plus 2 ions by molar concentration of Cu plus 2 ions. If we modify this formula for all the reactions, then generalized formula will be E naught cell is equal to 0.059 by n log Kc. So this is the Nernst equation for equilibrium constants. So standard electrode potential of the cell is equal to 0.059 by n log Kc. Here what is 0.059? We have already discussed 0.059 is the value of 2.303 into R value 8.314 into temperature 298 Kelvin by Faraday 96,500. On modifying this, on simplifying this value, we got 0.059. That means 0.059 is the value of 2.303 RT by N. RT by F. So whenever it is required, we take this part to discuss, right? It can also be written as standard electrode potential of the cell is equal to 2.303 RT by F log Kc. So this is the formula for equilibrium constant. It can also be written as E naught cell, standard electrode potential of the cell is equal to 2.303 RT by NF log Kc. This is the generalized form and this is the modified form. So you can use both, any one based on our convenient. Whenever it is needed, we use the modified form. Whenever it is needed, we use generalized form. Okay, dear students, now we are going to discuss last topic of this discussion, that is relationship between electrode potential and Gibbs energy. Relationship between electrode potential and Gibbs energy. What is Gibbs energy? That you have studied about Gibbs energy in 11th class in the chapter thermodynamics. Gibbs energy or Gibbs free energy is the amount of energy required to do some useful work. But the Gibbs energy cannot be determined individually, so we use generally change in Gibbs energy in our general discussions. So work done during electrochemical process is given by delta G is equal to minus NFE. Work done during a electrochemical cell is given by delta G is equal to minus NFE. What is delta G? Delta for change in Gibbs energy. Change in Gibbs energy. And N is number of electrons transferred during the electrochemical process. F is Faraday, whose value we know 96,500 coulombs, and E is electrode potential of the cell. E is electrode potential of the cell. But when electrode potential of the cell becomes equal to standard electrode potential of the cell, then delta G becomes equal to delta G naught. Means change in Gibbs energy becomes equal to standard change in Gibbs energy. So if we substitute these changes in the previous equation, that is in this equation, then we'll get delta G naught is equal to minus NF E naught. E naught of cell. That means standard change in Gibbs energy is equal to minus NF standard electrode potential of the cell. Now we know that from the previous discussion, standard electrode potential of the cell is equal to 2.303 RT by NF log Kc. So this was a small relation that we have discussed just before this. That is relationship between standard electrode potential of the cell and equilibrium constant. That is E naught cell is equal to 2.303 RT by NF log Kc. On substituting this in the previous equation in the place of E naught cell, then we get delta G naught is equal to minus NF into, in the place of E naught cell we can substitute this part, that is 2.303 RT log Kc. Here 2.303 RT by NF is the NF, right? Now here there is NF in the numerator, here also NF is there, both can be cancelled. So finally we get delta G naught is equal to minus 2.303 RT log Kc. So this is the relationship between standard change in Gibbs energy and equilibrium constant. This is also one of the very important concepts. But this part of Nernst equation and Nernst equation in terms of equilibrium constant, that is this one, E naught cell is equal to 2.303 RT by NF log C, and relationship between delta G naught and equilibrium constant. All these formulas are very, very important for competitive exams like NEET and JEE. But when it comes to board exams, occasionally we are getting numericals based on these concepts. But most of the students by heart these formulas and try to solve the problems. But this is not a good way. We have to understand the formula, we have to understand each and every term included in that formula. Then only we can easily solve the problems. So dear students, watch the video once or twice, take a notes, try to understand. If you feel any difficulty, please tell me in the form of comments. Thank you for watching the video. Bye.